move to a place of the world where I think we are still a fair throw away from the perfect warning chain. So we're still, I think, struggling with the very first mountain there, and that's tropical Africa. Before I start, I should acknowledge Waves to Weather, the Waves to Weather project that funded most of the research I'm going to present. And of course, various people have contributed to what I'm going to show, so I'll mention those along the way rather than here on the title slide. So I'm going to address three central questions in this talk. So why care about African rainfall? How good are current forecasts, and how to improve them in the future? So I care about African rainfall. So this region is frequently subject to flooding. On the photograph there, you can see a picture from Ouagadougou in Burkina Faso in September 2009, when pretty much the entire city was 1 meter or so underwater, with substantial impact on the population. In addition, of course, there's a large dependence on rain-fed agriculture. So not only the extreme rainfall, but also the more ordinary rainfall is very important for people, and there's not much in terms of irrigation systems in the place. So if we had skillful precipitations on the, say, 1 to 5 day timescale, we could certainly improve hazard prevention and food production, but also there would be benefits for things like hydropower energy production, which is important across the region, water resource management, disease prevention, road safety, and so on and so forth. There's lots of good socioeconomic reasons to look into this problem. So how good are current forecasts? In the framework of Waves to Weather, we recently published 2 papers, both led by my PhD student Peter Vogel. So the 2018 ones was more specific on northern tropical Africa, whereas the 2020 one that just came out is kind of expanding the type of analyses to the entire global tropical belt. So let's look at rainfall occurrence first. This is defined by a simple 0.2 millimeter threshold. This is ISMWF 1 day, so 24-hour forecast, and this is the raw ensemble. And we're comparing the direct model output here to what we call a probabilistic climatology based on TRIM. So pretty much we take observations from the TRIM period and then a few days plus minus around the day of interest to build a PDF of rainfall. And then we use this as a kind of ensemble prediction. And what you can see is the picture is very red. So lots of areas with negative skill, particularly the drier parts of the oceans, mountain areas like the Andes, and also relatively large parts of Africa. So there's substantial problems with the model here to distinguish between a rainy and a non-rainy day, even in an ensemble sense. If we move on to amount, the map gets a little less red if I switch back and forth. You still have the dry areas of the oceans and the mountains, but now you can see there's really significant problems over entire tropical Africa to the west of the East African highlands. This is now measured, I should say, by the continuous ranked probability skill score, so evaluating the entire ensemble distribution. So in this paper, we applied statistical post-processing to correct for some of the biases and dispersion errors we find. And again, I can toggle back and forth, and you can see there's improvement pretty much everywhere, and the red colors disappear. But tropical Africa in particular remains white on this map, and that means as it stands from a global ensemble prediction system at the moment, we cannot provide a model forecast, the one-day model forecast, better than a simple climatology to the hundreds of millions of people who live within this ellipse on the map. And I think for a meteorological community, that's an almost embarrassing result, I find. When we look at extremes, so potentially high impact weather, here defined by a threshold of 20 millimeters per day, again, 1 day ISMWF raw ensemble, we see a fairly similar picture of a lot of negative skill over tropical Africa. and you can post-process some of these problems away, but still you can see the map is essentially white. So no real skill in the model here at all. And you can also see that Africa stands in stark contrast to places like India or tropical Australia, where we have much better skill. So what can we do? And this is an overall pretty disappointing result. And I think the usual candidates are better observations. I mean, that's one of the themes of this webinar. But also there's questions of better data assimilation or just higher model resolution. So far, there's very few regional models in Africa with high resolution, better model physics, or even statistical prediction methods that take into account observations to train those models. So I will quickly step through those 5 points to give some perspective on where we should be going. I assume several of you have seen maps like this. There's not a specific day. This is a random draw from the ESMWF data coverage page with respect to radiosondes. And you can see there's very, very little across most of tropical Africa there. And that's kind of representative. This is not an extreme day. So for this part of the world, we're really enormously reliant upon satellite information, but with relatively little ground truth. We also sometimes don't know how good these satellite information actually are. So as part of the DACIWA, the EU-funded DACIWA project, we ran a radiosonde campaign in West Africa in the summer of 2016. So during 6 weeks, we launched about 900 radiosondes from the stations shown in the map here. And in the aftermath, we ran data denial experiments with the ESMWF operational system. And on these maps here, you can see differences between the system with the radiosondes and without. Left-hand side is 925 hectopascal winds, and you can see, particularly over the western part here, there is a substantial overestimation of the monsoon flow, so the southerly monsoon flow by the ESMWF model that's corrected by the radiosondes. And you can see on the right-hand side that if you have too strong monsoon flow, you have too strong cold advection from the ocean, and therefore you create a statistically significant temperature bias. Again, that's corrected here in the downstream area by the radiosondes. And this is the analysis, and of course you would hope that such changes had an impact on forecasts too. But if you look at the kind of evolution with lead time, the solid lines here is the runs with the radiosonde, so they start from an RMSE of 0, and the dashed ones are without the radiosondes. You can see the gap in the analysis, but it takes order, say, half a day or so for those two sets to catch up. So there's relatively little influence of the observations on forecast, suggesting that either the system is very chaotic or that there's still too large deficits in the model itself. And that's also to be found in rainfall. This is now the one-day rainfall forecast with the sondes on the left-hand side and without on the right-hand side. So this is the bias with respect to trim, I should also say. And again, I leave it for you to compare the two maps. There's not a super obvious improvement. At best, I think you see some improvement over the downstream Sahel here with the sondes, but it's not a very large impact here. So one of the things we hope for improvement is Aeolus, a satellite that was launched in 2018 with a Doppler LiDAR in space. And that closes an important gap in the observation system, because now we can, for the first time, observe winds in the tropics in cloud-free areas. And a PhD student of mine, Maurus Borny, has started analyzing data impact experiments by the ESMWF. And we found a relatively large impact on the African easterly jet. So we are still investigating this at the moment, and the hope is that through this mechanism, we can also find some improvement on rainfall predictions and other fields. Next candidate on the list is data assimilation. I'm not going to say very much about this, but I think it's well known that data assimilation systems in global models, they mainly use error structures typical for mid-latitudes. And this is just one of the reasons why typically we find a maximum in the analysis error in the tropics, as shown in this paper by Privy and Errico for temperature, but you can find such patterns for other fields as well. So again, as part of Waves to Weather, we have a new project that experiments with energy and entropy conserving data assimilation approaches specifically in the tropics in idealized experiments to see whether we can achieve some improvements through modifications in data assimilation. Next candidate now, higher resolution. Sometimes when you talk to people, it sounds as if as soon as you go beyond convective parameterization, all problems will just magically disappear. I don't think that's quite as easy. This is not a silver bullet, and I just show you one example here from a recent study by my postdoc Gregor Pante. So on the left-hand side, you see the bias in ICON with convective parameterization at the operational resolution of 13 kilometers. You can see fairly large biases here over the Sahel and also over some coastal areas here of Africa. If you move to higher resolution and switch the convection scheme off, you can see, in fact, particularly over the Sahel, where we have very large organized convective storms that create a lot of problems with parameterizations, there is a clear improvement, but there's also some areas where storms are triggered by more local processes, land sea breeze or complicated boundary layer mechanisms, where there's actually a deterioration of the model performance here. So it's not quite that simple. An interesting outcome from that same paper is that in the model with the parameterization, the red dots here, when you compare to radiosondes, there is quite a large moisture bias throughout the entire free troposphere. And we think this is because the parameterization tends to detrain way too much moisture into the atmosphere. When you go to explicit and enhance the rainfall efficiency, you have a much better match with the radiosondes, and we found in the paper that there are some positive impacts then also on long wave radiation, temperature, pressure, circulation, and so on. So these things are all very closely connected, and we have to kind of get the full package right to improve forecasts. So this leads to better model physics. I said switching the convection scheme off is one important step, but there's also a lot of problems with the boundary layer, for example. And I think to improve that, you really need field campaigns. You really have to go to the places, as we did during Dakiwa here, for example, in Benin, and set up a lot of instrumentation and collect very good data. And with that, you can produce things like we see on the right-hand side here. So a very detailed, quantitative, conceptual model of the different stages in the diurnal cycle, for example, of low-level boundary layer clouds. And this is where we are at the moment. I think in the future, we need high-resolution modeling experiments, ideally with data assimilation, to really find out why there is such a bad representation, for example, of these low clouds in many models. Right, the last point on my list is statistical prediction methods, and I think a lot of people say, oh, NWP has moved on, and has improved to a degree that these things, there's no place for such things in our world anymore today. And we found again in Waves to Weather this is not entirely true. So again, Peter Vogel, he played around with simple statistical models over the Sahel. So what we see here is a time series from July to September 2016. It's the probability of precipitation on the vertical axis. So the gray means the days when it actually rained. The black dots is the raw ensemble forecast from ISMWF. You see a lot of days with 100% rainfall probability, which then in the end, in some cases, did not verify. The red line is the climatological probability of precipitation. So that's kind of ranging about 50% rain every other day. And now the orange line is the dynamical model forecast, but statistically post-processed. And you can see how significant the improvement is from the black to the orange here. And then the blue line is a statistical prediction model, so based on logistic regression. And that the only input this model is taking is rainfall observations from the previous day. So there's no model in here at all. This is pure statistics, and you can see that the performance is actually surprisingly good, because in Africa there are these coherent rainfall systems that propagate over several days, or African easterly wave disturbances that propagate. So if you compare the two on the map, so this is now the statistical model compared to the climatology, you can see improvement everywhere, or neutral results. So that's good. That means there is actually an added value compared to the static climatology. If you compare to the post-process, you can see that in the wet part of West Africa, where we have a lot of propagating systems, there is a substantial improvement here. So just by knowing where it rained the day before and the day before that, you can make a much better forecast than even a post-processed dynamical model. But in the outer tropics here, where rainfall is more episodic and where there's a stronger influence from the more predictable extratropics, the post-processed dynamical model wins. So I should come to an end. I hope I could convince you that tropical Africa has an urgent need for better rainfall forecasts. Current operational products are pretty poor over most parts of the regions. Statistical post-processing can cure some of the problems, and I think we should do this operationally, not just kind of in a research project like this. If we could increase observations, that would be good for a lot of things, model development, verification, and so on. But the impact on forecast, for example, from radiosondes is not spectacular. Maybe new satellite missions have a little more promise here. We need to work on data assimilation. We need to move to convection permitting resolution as soon as possible, but this will not solve all the problems. We need to move on model physics. That's the hardest bit. We need good observations for this, and we also need, weather services that look more specifically into problems in the tropics. And last but not least, at least for the time being, there seems to be some promise in also building statistical prediction methods, at least as a complement for some parts of the tropics where other methods fail. Okay, that's all I have. Thank you very much. And I would, of course, be happy to answer any questions.
Peter, thank you very much for the very nice overview, particularly also how observations in several different venues can help to improve forecasts and predictions. I guess we have time for hopefully a couple of questions for you. Martin?
There's one question from Bob Goldhammer. How frequently do hailstorms occur in tropical Africa? Do you have any experience with that?
Yeah, good question. Over the lowlands, practically never ever, only over the highlands. So areas like Kenya or Ethiopia, I think they have occasional hailstorms, and then you get some damage for crops and so. But most of the, let's say, West African lowlands, for example, it's too warm for hail.
And maybe two other quick questions. The first one would be from Shira. Is the statistical prediction model grid point based, or are spatial coherence also taken into account?
No, this is grid point based. Pretty much what we do is for every grid point, we find another grid point that shows the highest correlations with the previous days and the day before this rainfall. And then we just fit a logistic regression model. So it's very, very simple, very, very basic. I mean, the Peter Vogel programmed this, I think, in 2 weeks. But we are trying to refine this now with more predictors and more sophisticated statistical tools, and we're looking a little bit into spatial coherence of the models being trained as well. So I think there is definitely scope for even better forecasts based on observations alone. But I think in the longer run, we would like to combine observational and model generated predictors to maybe get, you know, the best of both worlds in the end.
Okay, last question from Manos. Do we have an idea of the relative contribution of large-scale dynamics like MGO, etc., versus local dynamics to how poor the forecasts are in this area?
Yeah, good question. So in those future models that we would like to train, we will of course take things like MGO into account. Over Africa, the impact of the MGO is not huge, not comparable to, say, the Indian Ocean, West Pacific. But for example, in the more equatorial regions, we know there's a large impact of Kelvin waves, for example. So I think these definitely need to be taken into account. Over the Sahel, we have the African easterly waves, which are more synoptic scale, which seem to be the most promising candidates for, well, in principle, the dynamical models too, but they all have some problems with those. So we will see how far we can get with the statistical models taking those wave modes, including the MGO, into account.
Okay, thanks. There's a couple of more questions in the chat. Maybe you can have a look later.
Okay, thanks very much.
Thank you, Peter. And now